So I'm assistant professor in EC in University of Southern California. Today I'm going to talk about neural networks, the quantum ones. Right, so what are quantum neural networks? Professor Haar has already introduced us a few of them. And so basically we are looking at this so-called parameterized circuit where there's a quantum circuit and you can control a few parameters, and the quantum circuit will produce a quantum state which you can measure on. For example, you do Pauli measurements, and based on the measurement results, you can try to do classification, or you do supervised learning, and or solve eigenvalue problems. So when the circuit depth is becoming large, we call it controllable. Basically, the circuit is universal. So this should be true regardless of what type of ansatz you choose. For example, you can choose hardware efficient ansatz, random Pauli ansatz, or quantum alternating operator ansatz. And our results should hold for this circuit when the large depth limit. And they are widely useful for many different tasks. For example, these are useful to solve quantum chemistry problems when there's a hard Hamiltonian that you want to solve the ground state. And also you want to prepare some quantum states that are highly complex. Or you have machine learning problems that you want to encode information into classical information into quantum device and quantum states, and then you try to do classification and benchmark with classical performances. Alternatively, you can also think about quantum sensors. If the signals are physical layer signals and these signals get picked up by these quantum sensors, in general, you would want to have a parameterized circuit for preparing some quantum state probe and the parameterized circuit for measurements to get the best performance. So when you have parameterized quantum circuits, you have to do some training to make it work, just like the classical versions of them. So in this training, you have a lot of things you can pick. You can pick different loss functions, linear, quadratic. We look at the quadratic loss functions because it's quite general. It can be used for not only just solving the eigenvalue problems, solving the ground state, but also you can use this to solve classification problems and supervised learning. So that's what we look at. And we already have, people already have a lot of results on these quantum neural networks because they are very useful. For example, people know that if you randomly initialize the circuit, the gradient is not going to do well. It's going to be exponentially small in the system size, as these curves are showing, as the number of qubits increase. So that's not a good sign. On the other hand, assuming that your random initialization, you can also show that the error of this training problem is going to decay exponentially as time goes on. This is the result from this quantum neural tangent kernel, which they call frozen-kernel phase of training. However, there's a common issue in these results as they rely on Haar randomness assumptions, which is only true at the initial random initialization. Because as the circuit trains, you want these circuits to do some tasks. And to complete a task, there's already constraints implicitly being completed. For example, you are preparing a particular quantum state, then the circuit has to guarantee that the convergence towards that quantum state is happening. So it will deviate from the Haar random initialization, as we will show in this work. So in this work, we've taken a perturbative approach or first-order analysis of quantum neural networks with quadratic loss functions. And we obtain generalized nonlinear dynamical system equations that effectively describe these training dynamics, and which we can actually exactly solve and tell you when this will converge polynomially, when this will converge exponentially. And then we can, these models, of course, if you want to describe a quantum system by a classical one, there has to be assumptions. And we justify these assumptions by this so-called restricted Haar ensemble interpretation. As we said, initially, the circuit is Haar random. Maybe you can model it correctly. But later on, as the training goes on, these will deviate from Haar random and become so-called restricted Haar ensemble with constraints. And then we can also interpret these results.
Quntao?
Yes.
This is very, oops, I cannot understand what you're doing here. So can you describe us what actually you're computing? Like,
Sure.
what you're actually doing?
Sure. Because here we are doing general, let's say, we haven't specified any task yet. The next slide you will see a task. Here it's general training, so meaning that.
I understand, but what, general training, what does it mean? I don't even know what general.
So we are trying to minimize the loss function, which is quadratic constructed here, which is.
No input.
We can have input later on. In this case, we'll start with, let's say, trivial input state, and you are just minimizing a cost function. Depending on how you construct cost function, you can do different tasks, including solving the minimum eigenvalue, or you can do supervised learning. You just need to construct the right cost function, the loss function.
But for supervised learning, you need inputs.
Yes. There you will have multiple states and a multiple target, and then we will talk about that later. Yeah. So to begin with, let's consider a specific task of solving the minimum eigenvalue of this Hamiltonian. This is a toy problem of XXZ model, where the Hamiltonian looks like a bunch of poly X, poly Y, and poly Z. And there were these J parameters you can tune. So we pick certain system, let's say 6 qubits, J equals 2. So we know we can exact diagonalize and solve the minimum eigenvalue is minus 22. These are just small systems. And then we try to use the quantum neural network to solve the problem instead of just the classical exact diagonalization. So what cost functions would you like to use? Well, choice one is maybe we can just do a linear loss function. So you just set the loss function to be equal to the observable O. Or you can do a quadratic loss function where the observable O, expectation value, gets subject as O0, which is the target value you want to achieve, and then you square it. In this case, the observable O is just the Hamiltonian itself. So in this preparation of ground state, if you choose a linear loss function, this is what you will get in the training process when you use this gradient descent to update parameters to minimize the loss function in this quantum neural network. The loss function exponentially decay with the training time, which is good.
This is finite sample?
This is assuming the short noise is suppressed to 0.
So it's infinite shot.
Infinite shot. Later on, we will have experiments where there's finite shot considering. And now, let's say, what if you want to choose a quadratic loss function instead of the linear one? Because in this case, let's say we give you the knowledge that you know O0. O0 is the ground state, and you're guaranteed that it is minus 22. And you input that, and you try to prepare it. However, suddenly the convergence becomes polynomial. It's much slower. It's this green curve here, right? So what happened? And this is going to slow you down if you don't solve it. And fortunately, if you further tune this O0, the target values, let's say, to be below the ground state energy, so you are shooting for something even lower. And that gets you actually a faster exponentially decay now. So you're getting away from the polynomial, but going to exponential decay again, which is good. So this is saying that just choose the same loss function of quadratic form. Depending on what target value O0 you pick, this can become polynomial, exponential, and hopefully you want to optimize the design so that the convergence is good. So this is how we get started on this work. We basically did another task and find similar phenomena. And the hand-waving explanation is that, here we are doing a optimization, minimization of this loss function L, and the L is a quadratic loss function where observable O, expectation value, is difference of these two O0 and squared. So the hand-waving version of explanation is that in this gradient descent process, the gradient let's say, partial x of the loss, it's going to give you a O expectation value minus O0 term because of the quadratic construction. And then here we see there's a so-called arrow-kernel duality, where this is the residue arrow, and this is the gradient, or the kernel. So if O0 is actually equal to O min, you unfortunately will have a vanishing gradient. And this vanishing gradient overall will give you a very slow convergence, which is polynomial. It's not necessarily easy to see why it's polynomial, but it turns out to be polynomial. And if O0 is smaller than O min, then luckily this first term, O minus O0, will not vanish. And therefore, hopefully, the second term doesn't vanish. Then you get a good non-zero gradient, and it will actually exponentially decay the convergence. So in order to build these hand-waving arguments into rigorous results, we need to introduce the mathematics behind this. So we have a loss function again. We consider a quadratic one. Let me try to make the pointer. Okay, high laser point, good. So this is the loss function you have. And then in gradient descent, you updated the parameters of these quantum neural networks by this eta, the learning rate, multiply the gradient. And you can easily find it's a function of this arrow, epsilon. And then you do a Taylor, assuming small learning rate, you do a Taylor expansion of these update rules. You get first order and second orders. And the first order, you get this thing called kernel, or the quantum neural engine kernel, people call it that way. It's basically the amplitude square of the gradient of arrow. And another thing we call dqntk, so it's the next order thing that will appear. It has something to do with the Hessian multiply the gradient, left and the right. So Hessian is the matrix sandwiched in the middle, sandwiched by these gradients. So these two quantities will determine how these arrows decay overall. And this is to summarize the observation here. We are plotting the arrow and the kernel throughout the training process. For example, that XXZ problem, depending on how you choose O0. If O0, the target value, is actually larger than the minimum ground state, so you're targeting at some, maybe some states, excited states, you have an exponentially decay arrow, and the kernel is frozen, so which people previously call frozen kernel phase, so you can converge exponentially. And when you choose the target value right at the minimum eigenvalue, then unfortunately both quantities will only decay polynomially as 1 over t. Then if you decrease the target value below O min, then again you will have an exponential convergence of the residual arrow. However, because you set the target value to be something that is not achievable, so the actual deviation from the target value is a constant. It's just the ground state versus O0, there's a constant gap you cannot cross. So that's what's the phenomena being observed. And to explain that phenomena, we need to look at these equations describing the decay of arrow and kernel throughout the quantum neural network training process. And this is the leading order results, where this arrow multiply kernel here, and there's an arrow multiply dqntk. So it turns out that we need to really study how does the kernel and arrow evolve. We'll have to also deal with the dqntk, which is higher order things. And then dqntk you can further expand into higher order. So it seems like it will never stop. So quantum physics is, in principle hard, right? But it turns out we can do a assumption here, which is the higher order thing is actually not going to change much. So, and this is true at late time. We verify this numerically. So assuming that the ratio between the dqntk over the kernel is going to be a constant, which we can numerically verify in a lot of different training examples. So the y-axis is this ratio we are talking about, and x-axis is the time, and they do go to constant during the training. And we can also later on talk about ensemble theory to describe these quantum neural networks at late time to actually justify this assumption of constant ratio. So assuming this ratio is constant, suddenly then this perturbative formula becomes self-governed. There's a arrow and there's a kernel, and then this is actually a solvable system. And this system turns out to be the so-called generalized Lotka-Volterra model, which is a model that describes species competition with finite food. So some species will die, some species will not. And here, this arrow and kernel are like the two species, and they are, unfortunately, in this case, one of them will die. And so starting from the early time, because this equation is actually can be solved exactly in the so-called single data case. Later on, we'll have more complicated equations that we don't know how to solve, but we can only perturbative solve. This case, luckily, you get conserved quantities throughout the evolution. So the kernel minus lambda multiply the arrow is actually constant. So the trajectory of this time evolution on this kernel arrow plot is going to be a linear line. This is very simple. So if you arrive at this so-called O0 minus equals O min case, it's the critical point of this dynamics, and this curve just goes to both 0. And if it's in this O0 greater than O min, then it's a frozen kernel phase. Then this linear line will go to a point, converge towards fixed point where arrow is 0 and the kernel is constant. And vice versa, you will go to a non-zero arrow and 0 kernel phase. And this can be explained also by bifurcation, what we saw, that tuning O0 from above O min to O min and below O min, this transition of the fixed points can be explained by this bifurcation understanding. So you just take that first order results of arrow dynamics, kernel dynamics, putting that assumption that higher order things doesn't matter, and then you can solve as a function of time. The partial derivative of kernel is a function of kernel itself. And then this is a classical bifurcation example that we will find on Wikipedia, and this is so-called the transcritical bifurcation. So this gradient of k value, depending on what c value, the conserved quantity is, has different behaviors. So when c is actually smaller than 0, then the only fixed point that is stable is going to be the origin here. And when c is exactly 0, this is also a stable fixed point. And however, this you don't have this large non-zero value up here. So everything here is actually negative. And when c is greater than 0, suddenly this origin, it becomes unstable. And now the stable fixed point is at a non-zero k. So this explains this transition from k going to staying here, being stable at 0 to non-zero value. And this is going to be a jump because this is a bifurcation process. And we can compare the quantum evolution simulated on classical devices versus this theory, and then at late time, they agree pretty well. This doesn't look like linear because it's log-log plot. We want to focus on the late time. You can see that early time, the dynamics certainly has deviations. But late time, this is holding very well. Okay, so up to now, we still have an assumption in the theory, which is this ratio between dq and dk and kernel is going to be a constant. But how do we really justify this from first principle, or at least better assumptions? Here, we need to take a look at this claim again about the early time versus late time difference. So through this training of these new quantum neural networks, these quantum neural networks learning things, it's picking up information about cost function. So it's not going to be random anymore once you train it many steps. So at late time, this is going to be deviating from the Haar random ensemble that you can assume initially. And in fact, you can verify from frame potential that this is indeed the case, as we will present numerically and analytically later on. But let's get an idea of how these constraints work. So you have a neural network representing this unitary U at late time. And you have multiple data, as Professor Hakan was asking. So each data can be mapped to a final state, psi k mapped to psi k. And this psi k, of course, need to satisfy this loss function. They are at least local minimums, so you will converge toward this state. So meaning that this U is not random anymore. You map certain input states to certain output states, and they are not going to change during the late time. So a way to write down these unitaries at late time would be you can take this input data in the row and the output data in the column. So this input data from 1, 2 to n will be those phi k's that you want to initialize with. And then this output data is psi k, output 1, output n. So this constraint meaning that this input have to be mapped to the output with high precision. So the unitaries will have almost 1 value here, and the phase is free to choose because the loss function doesn't concern the phase. So then this will be the constrained version of the unitary. These terms will be almost 1, and then there's a random phase. And the rest of the things, because the loss function doesn't really concern anything about other states, how it works. So then the rest part is fully random. And we call this restricted Haar ensemble that we use to model late time quantum neural networks. And in the one data case, which is the minimization problem we were talking about, then this phase also doesn't matter. So it's a simple case as 1 and Haar random V here. So we can verify this claim by these frame potentials. Frame potential is a quantity people introduce to quantify how random certain ensemble of unitaries are. And for Haar random, its minimum value is going to be k. So this frame potential is basically these trace of the unitaries sampled from the same ensemble and how much are they overlapping, basically. And then you take a higher power to have a case order frame potential. The minimum is achieved by Haar. So if you get the minimum value, then you know it's a Haar random. And we show that if it's restrict Haar, it's going to be larger than the Haar value, and we can get closed form formulas up to a summation and also some lower bounds on it. And these bounds works pretty well. We have numerical simulations from neural network training, and then we collect different initialization. How is the unitaries like at late time on different initialization and training? And we found these blue points, they align pretty well with the restricted Haar ensemble, which means that indeed at late time, you're going to deviate from Haar to a restricted Haar model and to high precision. This is the phase potential versus time in actual evolution. And we can see that in these phases that we care about, they indeed go to much larger value than the initial Haar random value. They go to about 7 in this particular small systems. And this restricted Haar ensemble is actually important because, for example, this kernel at infinite time, at late time, versus the target value behavior is only captured by the restricted Haar ensemble. So there's a target value dependent late time kernel value that will only be captured by the restricted Haar. In the Haar random, it will be just a uniform case. And we can capture these values of this ratio lambda and other quantities fairly well by modeling this restricted Haar ensemble and taking ensemble average values to represent typical values and the values that we are seeing in experiments. So this restricted Haar ensemble is able to justify this lambda being a constant, and this lambda being constant also agrees well with the numerics and the analytical. There's some deviation, but the overall trend is okay. And this is an experiment on the IBM quantum device. This was done 1 or 2 years ago, so the device wasn't that good at that time. We picked maybe not the best device. There's some noise in this experimental realization. Mostly, I think it's due to this depolarizing noise in the system. The short noise is low enough in this case. And this is 2 qubit small problem, and it's hardware efficient ansatz. And we can see when O0 is equal to O min, there's a very slow polynomial decay. It doesn't quite converge well. And then when it's above O0, so you're targeting at some excited states, indeed, you're going to see this much faster decay. at small scale, it's sort of hard to tell exponential versus polynomial, but you can see much larger or smaller arrows in later at late time. And there's a fluctuation, of course, in the system. It's quite noisy. And recently we did an experiment, which is on multi-data case, which is much better. I'll show you a few slides. So we also generalize the results to supervised learning, where there's a couple of data you're interested in. So you are looking at a certain input states, and then these input states get mapped to some output states. These output states want to satisfy this loss function, where loss function concerns each output state's observable values minus the target values. And in this work, we assume that these input data are orthogonal, and unorthogonal case can be generalized in future works. For example, this is a result of two data case where there's a target value O1, target value Y1, target value Y2. And depending on each target value, whether they are below the minimum value of this observable or above the maximum value of the observable or in between or at this line, you can classify the whole thing into 6 dynamics, 6 different types of convergence. Some of them are polynomial, some of them are exponential convergence. Those that are living under the boundaries are polynomial convergence, and those that are in this bulk, they are actually exponential convergence. And you have frozen kernel, and because there were multiple data, there's fixed frozen phases that we can find out. And for more details, you can see a poster by my student, now postdoc, Zhuang. And in the two data case, this bifurcation dynamics is still there, and it's actually a more interesting case because there were actually 2 variables now if you model it as a nonlinear dynamical systems. There were 2 kernel values and the 2 arrows. So eventually this is one case where you can use this so-called Poincare diagram to classify the phase and fixed points. And I will not go into the details. Basically, on this diagram, you're plotting the late time linear expansion of these dynamic equations. And depending on determinant of A and the trace of A, you'll get a stable versus unstable fixed points. And what's going on is in this region where determinant is positive and the trace is negative, you get a stable fixed points. And you can do that for all the dynamics, and you can do the fixed point analysis and find out which fixed points are stable, which fixed points are not, and do the full classification of these convergence dynamics. And this is another experiment on IBM quantum device with 2 data classification. There's a mixed frozen dynamics being confirmed here with much higher precision. There's very little depressing noise being found. Let's say these dash curves are just exact theoretical results without any error being need to be modeled. So these are just the formulas we can derive directly. And this experimental result agree with the formula pretty well. You can see a clear exponential versus a constant for the different arrows you have here in the mixed frozen dynamics. And in the critical frozen arrow dynamics, you have a polynomial versus a constant case. And this is a 2-qubit, 6-layer experiment, not a large scale. And we could plan to do a large scale ones, but we will need to take care of some error mitigation if you want to go larger depths. Okay. Finally, let me acknowledge some funding, and these are my collaborators on these works. Zhuang is my student, and currently he's postdoc in a group to finish these works, very nice works, and he's looking for a postdoc position. And Junyu Liu is now in U Pittsburgh, assistant professor there, and Xiaochuan is in U Chicago, Liang Jiang is in U Chicago, and we have positions open in my group doing different type of works. And finally, I just want to mention that USC has a school of computing, and they will be hiring the quantum in the future. Please, thanks all for your attention.
I think we have just time for one quick question.
I have a question about the, you showed a plot where there was target and the target was either below the minimum or above the minimum. So is the target, yeah, that's perfect. The target is fixed throughout this convergence process, right? It's not
Yes.
time dependent. So the
Yeah.
target is not time dependent.
Target is fixed from the beginning to the end.
Okay. This is just maybe a comment or something, but I'm curious, have you tried maybe, can you vary the target over time, and would you see an even lower convergence rate? And would you maybe, because when the target is above the minimum, you won't reach the true optimal value in that case, right? So
So if the target is below the minimum, although you cannot reach the target value, but it will reach the minimum achievable value. So you still converge to the state you want.
right. Okay, so which one is so the target is the O0?
Yeah, O0 is the target value, and then the O min is the minimum value of that observable you are looking at. Yes.
Okay, so you see the fastest convergence rate when it's above the minimum then, right?
Yes. So I think that's a good question. So let's say in this case, maybe you want to tune this target through the evolution, and maybe that will give you faster convergence. And depending on each target value, how long you train, or maybe it's continuous changing. So the dynamics, if you change it too fast, then maybe the dynamical equations here are not working too well. But if you change, let's say, gradually in some adiabatic fashion, then we expect that this still should work. Let's say when you are above, then it's exponential. Then you right at that point, if you train a few steps, that is polynomial, and then afterwards it becomes exponential again. So
exactly. That's my question. So I'm just curious if you could maybe set the target at if you could make the target time dependent, you could maybe keep it high, keep it above the minimum initially, and you would achieve this faster convergence rate at the expense of optimality, and then you could decrease the target as time goes on to reach the true minimum. I don't know.
Yeah, I think that's something that's worth trying. Yeah. Thanks.
Okay, so maybe let's leave the questions offline. And thanks, Quntao, again for his talk.